Christmas lights. There. Hello, Alejandro. Hope you can hear me. Shoot is with Zoom. Yeah. Because as you can tell, I got my other camera out because it's not saying that the Zoom that camera here is being read. Show up. Try. No, but it's trying to show that camera now. Good. Just put your name in chat. Yeah, I'm working at getting the camera up and running. I'm standing right in front of the camera. Can you see me? It's not showing.
We can't see you right now.
What?
We can't see you right now.
Yeah, screen frozen. So stop the video and start the video and see what happens. And we have blank screen. I don't know why we have blank screen. We shouldn't have blank screen, but we do. So let me try this camera. And it's a little cockeyed. And I can't see the computer screen from there. One is using all this great technology. That doesn't work. Isn't that lovely? I suppose. So do something weird. No, I don't want that. Quite load up. Yes. It's not telling me where we left off. No. This is a nice computer. Yeah. It is not a wonder. Good. All right, I didn't do that yet. How about, have we done the half angles? You know?
I was gonna say, he just messaged me to say he's on campus. So
Oh, yeah.
thank you.
We do the half angles? We should have. Oh, look, it's-
So it's not right.
It was nice to know. Signs, we haven't gotten there yet. The angles, we haven't gotten there yet. Product to some and some to product. You done double angle and half angle?
Right, you just didn't feel
I think
upset.
we're doing double angle.
Okay.
Yeah, I feel excited.
So what's that?
That's what I said.
It was not related. Like we're talking about shapes of prisms and the archaeological structure of that shape. That's why I was like, oh, but. Kids would understand that word like.
Well, yes. Just give me a little. This is my document camera that I used at home. Right after. Right after the Zoom, COVID started.
Present it.
Before I got a little tablet thing, so I didn't have to use that anymore. Then I got a little webcam. That was more portable than that. It's inadequate for what I'm using it for, so. But this is a better quality camera. So someone told me to do this. It makes it depend on everybody's. And so there actually an O and an R right there. O-R. People on Zoom can't see it. How lovely. Anyway.
Are you gonna draw the little circle for yourself first, so you know what the blind spot is?
No. But we're gonna use double angle formulas and find exact values. We're gonna use double angle formulas to establish identities and use half angle formulas to find exact values. Again, these are formulas, and I haven't posted them yet, but these are formulas that will be on a formula chart for y'all, so you don't have to memorize them. It's just realizing when you can use them and how you can use them is the only deal. All right, we covered this, right? Double angles. Where sine of 2 theta is 2 times the sine and cosine of theta. And then you have 3 different formulas for cosine of 2 theta. And the equations 3 and 4 are derived directly from equation 2. Because I know cosine squared theta equals 1 minus sine theta. Well, that's one of the Pythagorean identities. And sine squared theta equals 1 minus cosine squared theta. And so to get this one, I just substitute 1 minus sine theta, sine squared theta for cosine. And so that gives me 2 sines that I'm subtracting, which gives us this. And then I know that I substituted it up in here to get this one. And if I substitute 1 minus cosine squared in for sine here, then I'm subtracting 1 and I'm subtracting a minus cosine, which becomes plus cosine. So now I have cosine plus cosine, which is 2 cosine squared minus the 1. So it's just simple substitution and then doing the simplifying the expression to get those 2. It's like with the trig identity, the Pythagorean identities. The other 2 identities are derived directly from cosine sine squared plus cosine squared equals 1. And that's what these 2 are. I was going to start pushing this to see if it would advance. Okay. Now, find the exact value of sine 2 theta and cosine 2 theta when you know that sine of theta is pi. 5/6. And pi is between pi over 2 and pi. So you're in the third quadrant, which means cosine is going to be negative. All right, so to find this length over here, and it's going to be a negative value simply because of the quadrant we're in. You do the Pythagorean theorem here, 6 squared minus 5 squared is that 11? So we get a negative 11, negative square root of 11 down here. And so cosine of theta is a negative 11, square root of 11 over 6. Well, so they're finding cosine here. And they're doing the same thing they're talking about the same thing I was talking about, is that it's in the second quadrant, so cosine will be negative and sine will be positive. And they find that this distance here is a negative square root of 11. So that's the cosine of this angle, is a negative square root of 11 over 6. Right? Adjacent over hypotenuse is cosine, and opposite over hypotenuse is the sine. And so we just substitute, okay, so here they found that it's a square root of negative square root of 11. Okay, and there they did use the formulas to find that. And then the double angle theorem, right? So we're doing sine of 2 theta, which equals 2 times the sine of theta cosine of theta. I know sine theta is 5/6, and cosine theta is a negative square root of 11 over negative square root of 11 over 6. And so you're just multiplying 2 times 5/6 times a negative square root of 11 over 6, which becomes the negative of 5 square roots of 11 over 18. They don't show this, but this goes away with 1 in here, because 2 divides 2 and 6. So this 2 becomes 1, 6 becomes 3, and then 3 times 6 is the 18. Because sine theta is given. Okay, to find the cosine of 2 theta, then we would use the 1 minus sine squared, because we already know what sine is. And that's an easier number to use. This one. Keep looking for it. Just don't. So we're going to use the cosine 2 theta is going to equal 1 minus sine squared theta. So that gives us the cosine 2 theta is going to equal 1 minus 5 over 6 squared, which is 25 over 6. So this is 1 minus 25 over 36. And 1 is, I can rewrite 1 to be 36 over 36. So the denominators are the same and all the action happens in the numerator. So that is what? 1136? And guess what? If you take the square root of that, it's going to be this right here. Only it'll be, taking the square root of it, you get plus or minus, so that's okay. And so, yeah, they do that. Oh, I forgot the 2 times the sine. Oops, that changes things. Because now that's 18 in the denominator. Yeah, see what happens when I don't refer back to the formula. I always forget the 2's in these formulas. That's why I need the formula sheet in front of me when I'm doing it. Okay. So you have 18 over 18 minus 25 over 18. So 18 minus 25 is a -7. Questions? Right here, they're not showing you that you're squaring this to get this in here.
Yeah, they didn't show, they just did it.
They just did it. So that's one of the things I don't like about iLab and about these presentations, is they don't show every single little step.
Oh, I hate when you get that stuff.
And I try to.
At least you're this, we can ask you.
Develop a form, okay. Okay. Yeah, they have you develop this, a formula for this one, but it's kind of just an exercise. It's not something really useful. Letter A, however, we can find the formula for tangent of 2 theta. Well, I know the tangent of alpha plus beta. Right? The tangent of alpha plus beta, and this is just a case where alpha and beta are the same number. So the tangent, the sum of tangent, the tangent of a sum is the sum of the tangent of the two angles. So tangent alpha plus tangent beta divided by 1 minus the product of the two tangents, which is what they have here. Teach this formula, some of these formulas stick. Some of them, not all of them. Okay, but now alpha and beta are the same number. So it's tangent theta plus tangent theta over 1 minus tangent theta times tangent theta. Well, this is just 2 of them. And this is just squaring tangent. So there's our formula. Tangent 2 theta is 2 tangent theta divided by 1 minus tangent squared theta. Now, with the sine of 2 theta, they did not go through the process of developing that, because you can develop it from sine of 2 theta is just the sine of theta plus the sine of theta. So that's going to be the sine of the sine of theta plus theta, sorry, which is the sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. Well, these two are the exact same products, and you're adding them together. So that gives you 2 sine theta, cosine theta. So the way they derive this formula is the same way they came up with the sine 2 theta to get 2 sine theta cosine theta, and same thing with cosine. This one's losing. It's a losing battle. See if that's better. It doesn't have much like that. Okay, so cosine 2 theta is the same thing as the cosine of theta plus theta. And cosine, when you're adding, you end up subtracting, and it's gonna be, what is it? Oh, yeah. Cosine theta minus sine theta sine theta, which is cosine squared theta minus sine squared theta, which is the formula. And then you just do the, you can do the, what do you call it? Use substitution with the Pythagorean identities to get the other two. So it's really not hard to derive the double angle formula once you know the addition formulas, the sum formulas. Now for sine of 3 theta, they're going to write 3 theta as 2 theta plus theta. So now they're going to do the sum of 2 angles, which gives us sine 2 theta cosine theta plus cosine 2 theta sine 2 theta. And now right here, we have, this is going to be 2 times sine theta cosine theta times cosine theta. And for here, we're going to use 1 minus sine squared theta, 1 minus 2 sine squared theta, 2 theta, theta. Because we have sine here, we want to use the cosine of the double angle that has sine. And that's what they did. Oh, no, they didn't. I would have. But, oh, I know why. It's the next step. Because here I'm multiplying, so this is going to be cosine squared. 2 sine cosine squared. Using the distributive property in here, we have sine times cosine squared, and then we have sine to the 3rd. Well, I have sine cosine squared, and I have 2 sine cosine squared. So that gives me a total of 3 of those. I think we're done, right? Yeah, we're done there. Now, these are just other formulas for sine squared, cosine and squared, and tangent squared. Sine squared is 1 minus cosine 2 theta over 2. Cosine is 1 plus cosine 2 theta over 2. And tangent is sine over cosine. Sine over cosine, the denominators are the same, so they'll disappear, and it'll just be left with 1 minus cosine 2 theta divided by 1 plus cosine 2 theta. So we can always derive the tangent if we know the sine and cosine. Trying to remember how. Oh, yeah. Cosine 2 theta equals 1 minus sine squared, 1 minus 2 sine squared theta, correct? We have cosine 2 theta equals 1 minus sine squared theta. Well, I can subtract, oh, there's a 2 here, sorry. If I subtract 1 from both sides, I have a -1 plus cosine theta equals a -2 sine squared theta. I divide both sides by -2, and this becomes a -2 in the denominator, and this is a -2. So those go to 1. So then I just have sine squared theta. And this negative sign, I can multiply the numerator by the negative sign, and so it'll be 1 minus cosine theta, right? No, 2 theta. Sorry, I dropped the 2 again. 2 theta divided by 2. Or I could have added 2 sine squared. I mean, what? Yeah, I could have added 2 sine squared theta to both sides, and then subtract cosine of 2 theta from both sides, and then divide it through by 2. I still would have got, that's still would have gotten a set. And cosine is done in a similar manner. Because cosine 2 theta also equals cosine theta minus 2 cosine theta minus 1 equals cosine 2 theta. And then you just add 1 to both sides and divide by 2, and you get that formula. So we can derive these formulas from other formulas. But what happens when you take the square root of both sides? I want to focus in here. It's supposed to focus. It's blurry. It's not just because my glasses are dirty. So write an equivalent expression for cosine to the 4th that does not involve any powers of sine or cosine greater than 1. So it doesn't matter if we have 2 theta in there. What matters is the exponent on the sine or cosine has to be 1. So you can start by rewriting cosine to the 4th power to cosine squared being squared, right? Because we have a formula here for cosine squared. So cosine, anything to the 4th power is something squared being squared. Well, I know cosine theta squared is 1 plus cosine 2 theta divided by 2 from the previous formulas. And I'm pretty sure they're going to multiply this out. They're going to square the numerator and the denominator. The denominator is 4, so they pulled it out as 1/4, and then squaring the but I would have just written it as 1 fraction to begin with, because they're going to multiply in by the 1/4. The very next step is what they're going to do. So 1 squared is 1. 1 times cosine 2 theta doubled is 2 times cosine 2 theta. And then squaring cosine 2 theta is cosine squared 2 theta. That's a process of squaring a binomial, right? You square the first term, you multiply the 2 together and double it, multiply it by 2, and then you square the last term. Now, cosine squared, we're gonna rewrite this as this, but we're going to multiply 2 times 2 theta. So this will end up being 4 theta. So in here, Do they do that yet? No, they multiply it in by the 1/4 at this point. And again, I would write these as single fractions and not 1/2 times this and 1/4 times this. It would be 1/4 plus cosine 2 theta over 2 and cosine squared theta over 4. But there are reasons why they're doing it this way, because they're going to do this again like they did up here. So cosine squared 2 theta would be this in here. So they would rewrite that again as the 1/4 and the 1/2 cosine 2 theta don't change, but this changes. This cosine squared becomes 1 plus cosine of 2 times 2 theta divided by 2. Oh, that's just to the, that's 4 theta here. Now, they don't care that we have multiples of theta. What they care about is having an exponent of 1 on each of the trig functions that are being used. And in this case, it's all in cosine. And then we multiply, well, let me see, do they show how they do it? No. Well, they brought the 1/2 out, multiplied it times the 1/4 to get the 1/8, and then they multiplied in by the 1/8 rather than multiplying in by the 1/4. So it would be 1 plus cosine 4 theta over 8. And so this one becomes 1/8. And they're going to add 1/8. Do they have, okay. No, they didn't do it. They didn't show what they did here to get the 3/8. What they did was they added the 1/4 to the 1/8. 1/4 plus 1/8 is 2/8 plus 1/8, which is 3/8. And then 1/8 times the cosine 4 theta is 1/8 cosine 4 theta. And this is just using algebra and arithmetic. Once you're done with the trig identities, right here, we did the last of the trig identity maneuvers. And now the rest of it is just manipulating using the rules of algebra and arithmetic. Only I would show each step, and they don't. That sucks, doesn't it? Okay. Sine theta times cosine theta equals a negative 1/4. Okay, so it's hard to see that negative sign, and that's 1/4. And alpha is inside the unit circle. So it's once around in that revolution, the angle. Okay, so it won't be anything greater than 2 pi, and it won't be negative. Well, as they'll state here, it kind of looks like the double angle formula for sine, except it's not being multiplied by 2. Well, if I multiply both sides by 2, I'll get 2 sine theta cosine theta, and that negative 1/4 becomes a negative 1/2. And so this becomes this way. And 2 sine theta cosine theta is sine of 2 theta. So I can rewrite this as a single trig function, which is sine of 2 theta equals a negative 1/2. Now they go about it slightly different than I do. They attack one angle that gives us a negative 1/2, but there's actually 2 angles that give us a negative 1/2 for sine. But they attack one of the angles first and then the other one. Because if you remember from the unit circle, sine is negative in the 3rd quadrant and the 4th quadrant. Sine is negative in both these quadrants. And so to get a negative 1/2, the angle is either in this quadrant or in this quadrant. And they attack this quadrant first. And realizing the angle has to be between 0 and 2 pi, and that angle happens to be 11 pi over 6. Which is what, 330 degrees. And so 11 pi over 6 plus 2 pi k, where k is any integer. Because if I add multiples, any integer multiple of 2 pi, I'm going to wind up at the same place this angle is at. So we're talking about, we come here and then we add 2 pi, or we add 17 pi, or we subtract 23 pi. We still wind up on this angle, on this terminal side. Okay. And so that's what they do. They start with -1 for k, and then do they do 0? And then they did 1. Did they do 2? I'm not too sure. So 2 theta is going to equal that. Well, if 2 theta equals this, I'm just gonna multiply both sides of the equation by 1/2, so I'll get what theta is. So 1/2 11 pi over 6 is 11 pi over 12. 1/2 of 2 pi k is pi k. So 11 pi over k, that's this angle. It's a different color. That's this one side angle. No, that's not right. It's over here. Realize that sine of this angle is going to be positive, but because we're multiplying it by 2, that's why we wind up over here, and it's negative. So we're not too concerned about what sine of 11 pi over 12 is. What we are concerned about is what the sine 11 pi over 6 is. Because the sine of 11 pi over 6 is a negative 1/2. So theta would be 11 pi over 2. I mean 11 pi over 12. Or adding pi k to it. And so that's what they start with. They start with 11 pi over 12 and they multiply pi by -1, and so you get a negative pi over 12. And then they're going to use 0, which is just this angle. The first one takes us to this angle over here. This is negative pi over 12. No, negative pi, yeah, negative pi over 12. It comes over here, I'm sorry, I went the wrong way. So it's this one here. But negative pi over 12 is not in our domain. This one is, because that's the angle we were talking about in the first place. And then 23 pi over 12 is this angle right here. Right, because another 1/12 will give us 24 pi over. And did they do 2 times pi? Yeah, they did 2 times pi, which is 30 pi over 12, which takes us over to here, but that's going around 1.5 times. Or no, just 1 whole time. So this angle is more than this angle and this angle are not in our domain. So it's these 2 angles. Okay. So those 2 angles, and they're not talking about it yet, but here, 7 pi over 6, which is this angle here, also has a sine of -1/2. And so that means 2 theta would be 7 pi over 6 plus 2. And so they did the same process here with this one, multiplied both sides by 1/2. And 7 pi over 6 became 7 pi over 12, and 2 pi k became pi k. And now they're going to do the same thing by choosing -1, 0, 1, and 2 for k to see what happens. So when k is -1, they got -5 pi over 12, which is outside of our domain. Using 0, they get 7 pi over 12, which is in our domain. And using 1, we get 19 pi over 12. 19 pi over 12 is right here. And 32 pi over 12, 31 pi over 12, which is larger than 2 pi. So the first angle where k is -1 and the fourth angle where k is 2 are outside of our domain from 0 to 2 pi. So these are the 2 angles from 7 pi over 6 we get. So we have 4 angles here that when you double them, you get -1/2 for their sine.
A little.
It's just remembering that for angles, you can keep coming back to that same angle by adding 2 pi any number of times. And so you use this entire formula for theta to get what theta is. And then you pick numbers for k that take you outside of the domain and go through the domain till you're outside the domain again. Since it had to be greater than 0, then multiplying by -1 here would get you an angle that is less than 0. And then you did 0 because that would just give you this angle. And then you do 1, which gives you another angle in between 0 and 2 pi. And then you do 2, which takes you out of the domain. So you have 4 angles. The 2 extreme are outside, the 2 in the middle are inside. So you want to bound your answers. You're going to bound it with 2 numbers that don't fit. So the other 2 are the only ones that fit. The restrictions that we have. And so we combine those 2 angles from each to give us the 4 angles that when you double them, the sine will give you -1/2. See, this gives me 7 pi over 2, 7 pi over 6. This would give me 11 pi over 6. This would be, when I double it, it gives me 19 pi over 6. 2 theta is outside our domain, but theta is not. So it doesn't matter if I multiply theta by a number that takes us outside of our domain, because theta is inside our domain. And I can still take the sine of 19 pi over 6. 19 pi, wait, well, this ends up, no, 19 pi over 6. Which is about, yeah. Oh, that's, yeah, that's going around once and then coming back to here. Yeah, because that's going to be equivalent to 7 pi over 6. And then when I double this one, I get 46 pi over 12. No, I get 23 pi over 6. And 23 pi over 6.
Hold on, I have a question.
Yes.
Where did you get the 23 pi over 12 from? We had 31 pi over 12. For that last one with the K.
This is from the 11 pi over 12. So you end up getting 2 angles from 11 pi over 12.
Okay.
And then you get 2 different angles from 7 pi over 12, which were these 2. So that's where the 23 pi over 12 came.
So they're separated then?
Yeah.
Okay, got it.
We found which 2 first. We didn't find them all at the same time. First, we attacked 11 pi over 6 and found 2 of the angles. And then we attacked 7 pi over 6 and found 2 more angles. I wish someone asked these questions when I was learning this stuff. And I had to learn it without the benefit of pre-calc. I went straight into calculus. And so we started doing, in some of the higher courses, we started doing stuff with this, and I was totally lost because I had taken pre-calculus.
How did you get into calculus, sir?
Because I had good math background, supposedly. And it was over 12 years since I've been in college. So with that. So I did a lot of reteaching, teaching myself stuff that, or I had friends teach me of stuff that I missed because I didn't take college algebra or pre-calculus.
That's nuts.
And, but I had to pick it up along the way because we used it. I'm gonna ignore this part. I'm not gonna throw a problem like this at you. If you have issues with these and the homeworks, please bring them to my attention, and we'll either talk about them through emails or bring it up in class and we'll discuss it in class. Now, these are half angle formulas. Well, these aren't actually half angle formulas. If I take the square root of both sides, then they are half angle formulas. Okay, sine squared of alpha over 2 is 1 minus cosine theta over 2. Cosine alpha over 2 is 1 plus cosine alpha over 2. And tangent of alpha over 2 is 1 minus cosine over 1 plus cosine of the alpha. So it would be this formula divided by this formula. The denominators are the same, so they go to 1. So we're just left with this, with 1 minus the cosine divided by 1 plus the cosine. Okay. Now, I think the next slide. The next slide is the half angles. So they're just going to take the square root of both sides of the equals, both sides of the equal sign on each one of these. Here they lumped them all together under 9. But once they take the square root, they separated them out. So the sine of a half angle is plus or minus the square root of 1 minus cosine alpha over 2. Cosine of the half angle is plus or minus the square root of 1 plus the cosine of the angle over 2. And tangent of half of alpha is plus or minus the square root of sine minus cosine of alpha divided by sine by 1 plus cosine of alpha. Now the plus or minus, which makes sense, depending upon where the angle is, in which quadrant the angle is, determines whether these are plus or minus. Right? Sine is positive in 1 and 2. Cosine is positive in 1 and 4. Tangent is positive in 1 and 3. So that's how you determine where it's going to be plus and where it's going to be minus. So if I'm taking cosine of cosine of the half of 150. The half of 150 is 75 degrees, so that's going to be over here. And so that means this is going to be positive. Where if I did cosine of 300, which is over here, half of 300 is 150, which is over here, which means it's going to be negative. Even though cosine of 300 is positive over here, cosine of half of 300 is going to be negative. Okay. Now use half angle formulas to find the exact formula. Okay. So I kind of hinted to this. I knew they were going to use 75. So I can say this is the cosine of 150 divided by 2. And 75 is in the first quadrant, so it's going to be the positive square root of 1 minus the cosine of 150 divided by 2. Or cosine of 150. I remember that right? Is it minus? No, the cosine is plus. Screwing that up. Okay. Which is why I need the formulas in front of me. Which is also a reason I don't require you to memorize them. What's the cosine of 150?
Square root of 302.
Yeah, 150 is over here. And that is 5 pi over 6. So this is going to be the square root of 1 plus the negative square root of 3 over 2 divided by 2. And I'm just going to rewrite that divide by 2 as multiplied by 1/2. 1 minus the square root of 3 over 2, which becomes 1/2. This is 2 over 2, so it's going to be 2 minus the square root of 3 over 2. And the whole thing is square rooted. So now we have, and multiplied by the 1/2, you get 2 minus the square root of 3 over 4 square rooted. And now I can take, I forgot to do this the other day, and I forgot to square root 4 down here. So I have 2 in the denominator and the square root of 2 minus the square root of 3 in the numerator. Now, I can't take the square roots separately here because we're subtracting. So I would first have to find out what that number is and then take its square root. So this would be the exact answer. An approximate answer would be typing it into the calculator. So, yeah. So the plus sign we're using is going to be on the outside of the square root, not the sign in here. The sign in here depends upon where alpha actually is. Okay. And so far they've done it the same way I did. Only they didn't have to correct for using the wrong formula. And they got that, which gave them this, which gave them that. They didn't show what happened here along the way to get what they got. But, this up here. Okay. Now, for negative sine of, sine of negative 15, sine is an odd function. So the sine of a negative angle is the negative sine of the positive angle. So the sine of negative 75 would be the negative of the sine of 75. So we would follow the same process as previously, 75 degrees. So this sign, this negative sign here comes into play at the end. We carry it through until the end. So sine of 75 is going to be the sine of 150 over 2. So we have the negative here, and they went ahead and replaced the 75 with 150 over 2, and it's going to be 1 minus the cosine of 150 over 2. The sine of 150 and the sine of 75 is positive because it's in the first quadrant. And so this part would be positive. So this is what the sine is, and this is what the negative of the sine. So the negative sign is there. This negative sign is here, not because of the sine function, but because of the minus sign out front. If this angle had been, or this angle had been in the third or fourth quadrant, then this would be minus a negative. And so this would have ended up being positive. So that's something to be aware of, because MyMath loves to do that stuff. And then cosine of 150 is again the square root of 3 over 2, but it's the negative square root of 3 over 2 because cosine 150 is in the second quadrant, and cosine is negative there. So we're subtracting a negative square root of 3 over 2, which gives us the plus the square root of 3 over 2. And so it works out very much the same way as the previous problem. So inside, in the numerator, you wind up getting 2 plus the square root of 3 divided by 2 being divided by 2, which gives us a 4 in the denominator. And then you take the square root of the denominator. And that negative sign on the outside carries through. So the sign of a negative sign 75 is a negative value. Because if you think of negative 75, negative 75 takes us into the fourth quadrant, and sine is negative down there. So it would still follow. Okay. All right. Alpha is in the third quadrant. Sine and cosine are negative in the third quadrant. So cosine is negative because they're telling us it is, and they're telling us exactly what it is. It's a negative 2/3. So there's a couple of ways to do this. Let me see how they decide. Well, because you're gonna be using whatever the cosine of alpha is to find these, because sine of half of alpha is the square root of 1 minus the cosine of alpha over 2. And cosine of half of alpha is the square root of 1 plus the cosine of alpha over 2. And tangent of alpha, alpha over 2, is the square root of 1 minus the cosine of alpha divided by 1 plus the cosine of alpha. So we only need to know what the cosine of alpha is. And they give it to us. And I know the sine is negative and the cosine is negative, but tangent in that quadrant is positive. And if I divide through by 2, that means alpha over 2 is going to be between 2 pi and 3 pi over. Oh, that's going to be oh, that's going to be third quadrant. No. Pi over 2 to 3 pi over 4. Oh, that's going to be in the third quadrant. Alpha over 2 is in the third quadrant. So that means sine will be positive, cosine and tangent will be negative. Sine is going to be positive, and the cosine and tangent will be negative. So doing the sine of half of alpha formula, we know cosine of alpha is a negative 2/3. So 1 minus a negative 2/3 is 1 plus 2/3. 2/3, which is 5/3. 5/3 divided by 2 is 5/6. And so this is going to be the square root of 5/6. And they do something way wrong here. Tell me what it is. Their final answer here is incorrect. What's wrong?
The bottom,
Nope. What they did, they multiplied numerator and denominator by the square root of 6. But the answer is incorrect. What's the square root of 5? Is it 5?
No.
No, yeah. They botched that. This 5 should be 5 times 6, so it should be the square root of 30. Does that make sense? Because if I can separate the two square roots as the square root of 5 divided by the square root of 6. Okay. So I multiply numerator and denominator by the square root of 6. I'm multiplying by 1. And so my denominator becomes 6, which is what we wanted to have happen. And then I can multiply my radicands together. And so this is just the square root of 30. The square root of 30 has no factors that are perfect squares. I do not know who this person is who edited this, who proofread it, who actually wrote it, what they were doing.
so they do a lot of things right, but they can't do everything right.
Yeah, but some of these are so glaringly wrong. And you're supposed to have people who check your work,
Sir, you know Miss Trainer, right?
who always look for mistakes.
This storage trainer right there, the head of the history department. I have her book in my bag. There's so many mistakes in there. Her mouth, there's so many mistakes. She said, yes, I know, trust me. And you know, people go over her stuff. They read it, they proofread it.
There's a horror author, most of it's science fiction horror. And he wrote a book. He has a series. It's his GFL series, Galactic Football League. So it's football in space. And the latest book that came out is this. Okay, this series has elements of horror. It has major elements of football. It has elements of criminal activity, or crime, and it's space aliens. There's a race of sentient aliens that are known as the Squarno. I have no idea how to spell that. And they're human-sized cricket-like animals or beings that can jump very high, very far. So they're wide receivers in the football league. And they're hyperactive. So they're always bouncing. And one of their aspects is that they tend to turn their quarterback into a godling because they worship him because he throws them the ball.
Yeah.
Yeah, it's just a lot of, and so when you're talking typos, this went through several people's hands. Several people's hands. The front of the book, the dust cover jacket, the inside of the book, but they did not double check the spine. Because on the spine, it was spelled this way.
Ridiculous.
Well, this was an independent publishing deal. So he sent it off to a publisher, they published it, and sent it back to him, and he would send it out to the people who bought it. When he discovered this, I don't know how he discovered it. Someone told him, or he was looking it over after he got the final book. Didn't notice it while it came to him, and he was allowed to inspect it before they did the final printing. So he sent out a message to everybody saying, this is what's happening. It would cost too much and take away all of his profits, plus he'd have to pay additional money. So he'd be in the loss if he had it reprinted.
Yeah.
And so he just told everybody, expect it. And then the guy who did the cover jacket said, well, I'll do t-shirts. And on the t-shirts in a different color, there's this with a G put over it, right, like that. So yeah, it was sort of a joke. So I bought a t-shirt. Okay.
Oh, you have this T-shirt.
Yeah, I bought a copy of the book for both of my sons.
So you've read this stuff?
Oh, yeah.
Is it, I mean, would you consider?
That was book 6
So
or
you-
book 7.
It's good.
Yeah, I love this stuff. Scott Sigler.
Wait, sir, you said that you didn't have to take pre-calculus, right?
What?
I said, you said you didn't have to take pre-calculus, right? You just like passed it because of your background in math.
I didn't take pre-calculus.
So
Technically,
what did
they,
you take, like throughout your college years?
When I was in high school, I took 3 semesters of math my senior year. And so I was able to get into calculus when I went to college. Well, this was back in the early 70s, and the requirements were a little different to get into calculus. When I went back to school to pick up all my math hours, because I failed miserably my first time through college. Yeah, I was one of these people who was not ready for college when I got out of high school. I was ready for college when I was in my mid-30s, which is when I went back to school. I had already taken several math classes. I took Cal 1, 2, and I took set theory, and I took some other math classes. Set theory is the one that broke my back and told me I should get out of mathematics and go a different route. And so I did. I got a degree in geology, which I've done absolutely nothing with. So,
Wait, I thought you said you worked at like an oil rig once.
yeah, I did. I worked out in West Texas for 9 months.
9 months, sir.
9 months.
That's kind of a lot of months, in my opinion. That's like someone can hold a child in their stomach for like 9 months.
That's it.
That's true. Okay. But he's does a lot of, he's written several books. All of his books happen in the same universe. He's got 3 series out. And there's a number of independent books. But they're all written in the same universe, which means that they refer to characters or happenings that happen in the other books.
Yeah, that's nice. So do they ever bump into other characters from other books?
Trying to remember. Well, those crossovers are not to the point where you had to have read that book to understand their interaction in this book.
Okay, that's good.
But all of the characters in his books are named after bands.
Fans?
Bands.
So is there a read in there?
Yes.
Are you
And-
kidding?
In Nocturnal, which is pure horror, well, it's science horror. I'm a character in there
Sir.
who has Tourette's, and he's a fence. A fence. He buys and sells stolen goods.
Okay.
And his name in his character, he goes by the name Mr. Biznaz.
Uh-huh. Wait, but how is that you?
Well, that's what he calls himself, but his name is Thomas Reed.
Sir, how did this happen? Did you confirm that that's you? I mean, is it a
Well, yeah,
coincidence?
in the book, he says Thomas Reed, always also known as Mr. Biznaz.
Sir, how do you confirm that that's you? You? Does he know you or
I
something?
can't imagine there's a trillion, Thomas Reeds out there.
Sir,
I went to some of his book readings. I followed him in his forums. I became quite popular on his
You
website.
followed him home.
that's what I thought he was gonna say. I followed him home one day.
Well, I picked him up at the airport
Oh, wow.
and took him to the hotel he was staying at. I picked him at the hotel and took him to the was it a Borders? Yeah, to the Borders he was doing the book signing at here in town.
Yeah.
And he came here to San Antonio because of me.
Oh, God. This is too much, sir. Too much. It sounds more like a love story, sir.
Well, and then there's another author in Houston, Paulie Cooley. He does psychological horror like you wouldn't believe. I met him at one of Sigler's book signings, the first book signing I went to. And we started talking. He gave me his business card, which had his website on it, Shadow Publications. And I started listening to his stuff. He was creepy. He was about this tall, had black hair that went down past his butt, and was wearing a black leather trench coat.
Oh,
He looked creepy, let me tell you.
yeah.
And so we had a small conversation, and I started following him, and he put me in a book as a character. I followed him on Twitter and other places. And he put my name as a character in the book. And what it turns out is the book was about a character named Tony Hunt. He was a detective. And he thought he had a serial killer on his hands. And so he started looking at old files, unsolved murder files.
Yeah.
That fit this pattern. And so some of them were in his district and some were other places. And he found out that he found one cold case file about a person by the name of Thomas Reed. So I didn't show up as a character, I showed up as a file on a dead corpse.
Okay.
So so on Twitter, we were joking back and forth, and I said, yeah, I showed up in your book, but I showed up as a dead corpse. Not even a corpse, but as a file of about a dead corpse. And he laughed it off, and I called him a bastard, and he called me, and he said, okay, from now on, you're gonna show up in every book I write, and you're gonna show up as a corpse.
Oh,
And I
nice.
do.
Oh,
He did one series called The Black, and I showed up as a corpse twice in that one.
oh my gosh.
Yeah.
Oh, I caught him a bastard. Wow.
Yeah, in the book, in the Nocturnal book, he originally podcasted it, and then the publisher took it up and he had to rewrite it. But I showed up twice in the original podcast version. Once at the beginning as a teenage boy that got killed,
Oh,
and then at the end as the new chief of detectives in San Francisco.
well, that's nice.
And then in the rewrite, my character disappeared, so he gave my name to Mr. Business. And when he came on the book tour, I hadn't listened. I only consume books through my ears now. I hadn't come up to that part yet, so everybody there made sure they didn't spill the beans about me being in the book.
Oh,
Because he had told me that he had cut my characters from the book.
Yeah.
He didn't tell me he put in a new character, or he renamed a character.
that's pleasant part.
where that
So you got a
character-
promotion from a corpse to a character.
Well, I was a character that showed up at the end of the book, but it was like the last chapter. So, not very long.
In other words, the best part.
Okay. I got way off track there. Okay, so we're dealing with, letter B. What was letter B? It's been so long. Oh, cosine of alpha over 2, since cosine is, okay, so we're gonna use the cosine formula here. But again, since where alpha over 2 winds up, the cosine is negative there. And so this is going to be negative here. And we know the cosine of alpha is, what was that? A negative 3/2. So now this becomes 2/3. Sorry. I do that all the time. I switch the 2 and the 3 with 2/3. So 1 minus 2/3 is 1/3, and 1/2 of 2/3 is 1/6. And rationalizing the denominator, you get the square root of 6 over 6, so it's a negative square root of 6 over 6. And then they want the tangent. The tangent is just the sine over the cosine. So the sine was the square root of 30 over 6, and so we're going to divide that by the square root of 6 over 6, negative. Oh, this is just square root of 5, negative. Yeah, because we're still going to wind up with -5, whether we did it this way, or did we know that tangent is cosine over sine? So if I did the cosine over the sine, it's going to be the square root of 30 over 6 divided by the square root of 6 over 6. Because for the sine of 2 up, I think it was the square root of 30 over 6. And if we divide that by the negative square root of 6 over 6. All right, these 6's go to 1. And so this is, so that I'm still going to be negative. And so we're going to have the square root, and I'm going to rewrite the square root of 30 as the square root of 6 times 5 divided by the square root of 6. And so the square root of 6 here, well, I can write this as a single fraction. Let me do that. So we have the square root of 30 over the square root of 6 can be written as the negative square root of 30 over 6, which is the negative square root of 5. So either way, you get to the same place. I would have done this. Because I have sine of alpha over 2 and I have cosine of alpha over 2. Okay. So half angles for tangent. Okay, so this is another form of the half angle for tangent, not using the square root. So 1 minus cosine alpha over sine alpha, or sine alpha over 1 plus cosine alpha. Didn't they already give us a half angle formula for tangent, which is the square root? The square root of this being divided by this. So it'd be interesting to see how they work out to be that. Oh, yeah. Okay. Now, product to sum and sum to product formulas. You have the sine of the product of two angles can be written as the sum. And if you have the sum of two trig functions, it can be written as a product. So sine times sine of theta. Please notice these all look the same. All right, we have cosine alpha minus beta, we have cosine alpha plus beta, we have cosine alpha minus beta, we have cosine alpha minus beta, we have sine of alpha plus beta, we have sine of alpha minus beta. So it's the same thing, except at this point, it changes from cosine to sine. And the first one is the subtracting, and the third one, and the second one is adding. So sine times sine is going to be adding. Cosine times cosine is going to be, I mean, sine times sine is minus. Cosine times cosine is going to be plus. Now, something I disagree with what they, how they wrote this here. They didn't follow the same pattern as they did up here. If you do the commutative property, I can switch the order of these two, so they'll follow the same order those two do. I don't know why they didn't do that. So here we have the sign of that times the sign of the other, which become, was it one half times? Yeah. So we wind up with 1/2 times the sine of 50. Was it, did they do the minus first or the add first? I can't remember. I'm losing my mind. So the sine of 5 theta minus 3 theta minus the sine of 5 theta plus 3 theta, you multiply by 1/2, which gives us the sine of 2 theta minus the sine of 8 theta. And it's being multiplied by 1/2. And they might carry it on by doing the double angle formulas. Oh, it was cosine. I'm sorry. That's right, it was cosine. Jeez. Because, yeah, with the sine, it's gonna be, second. Number 1 and number 3 are for, oh, this is sine times cosine, and this is sine, and this is cosine. Okay. When it's sine times sine, it's the cosines. And when it's cosine times cosine, it's the cosines. But when it's sine times cosine, it's going to be sine. Okay. So that's where I screwed up there. It's going to be the cosine, which is just that. So they didn't do, they just rewrote to this. And then letter B, you're going to do the same thing, but instead of minus here, it's going to be plus. So it's going to be 4 theta minus theta, which is 3 theta. And then it's going to be 4 theta plus theta, which will be 5 theta. So it'll be cosine 3 theta plus cosine 5 theta. And it's going to be multiplied by 1/2. And then the third one, what was the third one? Was the third one sine times a cosine? Yeah. You're still going to add and subtract these two angles, but now it's going to be sine and sine, and you're adding, and we're still going to have it times 1/2. So the sine of the sum plus the sine of the difference And sine of a negative angle is minus the sine of the positive angle, so they pulled the minus sign out. And there we have it. Now, sum to product. Here, they're just introducing all these formulas and showing you how they can be used. So we're adding the sine of two angles. We're subtracting the sine of two angles. We're adding the cosine of two angles. We're subtracting the cosine of two angles. So what changes? Well, what changes with the sine is still going to be the sum divided by 2 and the sum divided by and the difference divided by 2. It just switches. If you're adding, it's going to be the sum it's going to be the sine of the sum divided by 2 times the cosine of the difference divided by 2. If you're subtracting the two signs, then it's going to be the sine of the difference times the cosine of the sum, both divided by 2. And you still have it 2 times that product. So you have it 2 times the product on all of them. Please notice when you're subtracting the two cosines, you're going to get a negative response here. All right, and cosine, when you're adding two cosines, it's going to be the cosine of the sum divided by 2 times the cosine of the difference divided by 2. And you double that product. But when you're subtracting, instead of being the cosine of both the sum and the difference over 2, it's the sine of the sum and the difference, both of them over 2. And you're multiplying by -2 now instead of +2. Don't haven't derived these in a long, long time. So this is just a matter of going back to the formulas and determining which one you're going to use. Here I'm subtracting 2 of them, so I'm going to use this formula. It's going to be the difference of the two angles divided by 2 and the sum of the two angles divided by 2, sine of the difference, cosine of the sum. And so that's what we do here with that one. And there we have it. Oh, okay. They divided by 2 and divided by 2. They reduce the fractions. And letter B. So we use this formula. And so we get 9/2 theta and 5/2 theta. And we can't simplify those fractions, so we're done. And we'll start with this next one. So if you have questions for me, now's the time to ask. And I'm sorry, I spent about 20 minutes talking about other things other than what I should have been talking about. I do that a lot. I used to do it more than I do this semester.
I do have a question. I was trying to catch up
Yeah.
with what I missed last week, but the videos.
Yeah, they haven't been posted yet. I meant to get those posted today, and I can't. I can post maybe one video in a couple of hours at school. That's how slow it is. And when I do it at home, they're pretty good. I'll post all the videos this evening. And I need to get those format sheets. to you.
Yeah, I was out last week, my work schedule was crazy, so my work schedule's gone through the roof, so I'm sorry about last week.
No, I understand, yeah.
All right, yeah, I'm gonna try and catch up.
Okay. Oh, there was one of those problems you sent, like the sine of 6 pi. Or this, no, the sine of 6 theta, where theta equals pi. Okay.
Now you're asking, I don't remember.
Well, what I thought it was, what they said it was, well, they said, I thought it would be 0.
Yeah, that was a really long one with Simon popping up all over the place. Was that the one of really long expression that ended up with?
I was doing other things when I got your email and started looking into it, so I meant to get back to it, but I haven't done that yet.
All right, thank you. There seems to be a lot of questions on the other chapters. There were many problems that were there. Are we supposed to do all of them or just pick some of them? The early chapters 1, 2, 3.
Oh, let me go in there and look at what's going on.
All right, all right. You say go in there, you mean the office or look at,
No, I'll go in and look into the, and I'll look at the assignments. And
all right, that sounds good. Thanks a bunch.
everybody.